Good evening, sir.
Yeah, good evening, Varunji.
Fine. How are you, sir?
I'm fine, sir. How about you, sir?
Sir. So with this, we have the speaker for third session on this 5-day workshop of Amalgam, applications of machine learning in signal, image, and vision processing. Let me give a brief introduction to today's speaker, Dr. Shivram Dubey. Dr. Shivram Dubey has been with Indian Institute of Information Technology, IIIT Allahabad, since July 2021, where he is currently the Assistant Professor of Information Technology. He was with the Indian Institute of Information Technology, IIT Shri City, as Assistant Professor from December 2016 to July 2021 and Research Scientist from June 2016 to December 2016. He received the PhD degree in Computer Vision and Image Processing from Indian Institute of Information Technology, Allahabad in 2016. Before that, from August 2012 to February 2013, he was a project officer in the Computer Science and Engineering Department at Indian Institute of Technology, Madras. Currently, Dr. Dubey is executing the research project funded by Global Innovation and Technology Alliance (GITA) India-Taiwan project. He has also executed the projects funded by DRDO Young Scientist Lab in Artificial Intelligence and Science and Engineering Research Board (SERB). He was a recipient of several awards, including Best PhD Award in PhD Symposium, IEEE CICT 2017 at IIIT Gwalior, and NVIDIA GPU Grant Award twice from NVIDIA. He received the Outstanding Certificate of Reviewing Award from Information Fusion Elsevier in 2018. He has also received the Best Paper Awards in IAPR, CVIP 2020 and IEEE UPCon 2015 conferences. The research interest area of Dr. Shivram Dubey include computer vision and deep learning. Today, uh, Dr. Shivram Dubey is going to deliver the talk on convolution neural network CNN for computer vision. With this, I now welcome today's speaker, Dr. Shivram Dubey. Over to you, sir.
Thank you very much, Varunji, for introducing, and a very good afternoon to all the participants as well. And I welcome all the participants that they find the time in order to listen this particular session. So I think I have shared the screen. Is it visible?
No, sir, your screen. Yes, sir, you have. Yeah.
So my slide is visible, right, sir? Hello. 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 Varunji, is it visible?
Yes, sir.
Okay,
Yes, sir.
thank you very much. Okay, thank you very much. So basically, this particular session is going to be on convolutional neural network for computer vision. So first of all, a bit about IIIT Allahabad. So IIIT Allahabad is one of the research-led institute of national importance, and there are many research labs in IIIT Allahabad that includes even computer vision, data science, machine learning. So there are many research labs which is set up. In fact, the master's program at IIIT Allahabad itself is being offered in very specialized area that includes human-computer interaction, robotics, machine learning, data science. So all these cutting-edge technologies which are growing. So all these technologies are actually part of the MTech program here. So I also belong to Computer Vision and Biometrics Lab, and Computer Vision and Biometrics Lab is executing projects funded from different organizations, including DRDO, DST, SCRB, Ministry of Home Affairs, and Geeta. And currently, even 3 international project is being executed in the lab, which is India-Germany project, in India-Slovenia project, and Indian-Taiwan project. Our lab is also very active in terms of organizing different flagship events. And in fact, we regularly organize one workshop here that is called ADA-SIVA workshop, that is Advances in Deep Architectures for Signal, Image and Vision Applications. And next year, we are going to hold 2 conferences. And one conference is International Conference on Computer Vision and Machine Intelligence, which is scheduled on 12th and 13th August 2022. And we are also going to have one more conference, IEEE section conference, which was organized just this year by this Varunji. That next time it is going to happen at IIIT Allahabad in December 2022. So coming to this particular session, so here we are going to see a little bit about convolutional neural network. What is this typical CNN architecture? What are different layers which is present in CNN, and what is the progress? And what are major what are the major advancement in CNN architectures that has happened for different computer vision problems like classification problem or object recognition problem, segmentation problem, or even this image generation problem. So this convolutional neural network, first of all, this is part of the deep learning, and we have seen a huge growth in deep learning in past 1 decade, especially in early days when deep learning was not there. Yes, in early days when deep learning was not there, then all these problems was typically being solved using machine learning techniques. But when we utilize the machine learning techniques, then generally it is a 2-step process, where in the first step, we used to manually find out the ways to extract the primitive features, or basically the features which is important with respect to the problem that we are solving. And that's what was entire research area in early days that was referred as the feature extraction techniques. So people used to find out different features which is basically responsible for better performance for a particular problem. So for example, suppose if we talk about computer vision problems, then features which includes color, texture, shape. So these features basically can be treated as some primitive features, and by utilizing such features, we can extract the features. And then those features were served as the input to the classifiers, and classifiers were being trained based on those extracted features. So what was the problem with these technique? So first of all, identifying which feature is important with respect to a problem, that was again kind of a very knowledgeable work, where if someone is having a great domain knowledge as well as feature extraction techniques knowledge, then only they can find out that what features might be important, and that too might not be sufficient to solve the problem. So that was one issue with this machine learning technique. And in deep learning, what has happened, the network, like neural network that we used to apply even as a machine learning tool in early days, kind of a shallow network. So what has happened in deep learning, basically this network is having more and more number of layers. Earlier also people tried to utilize deep learning, but they could not succeed. And the reason was the limited resources, computational resources, as well as non-availability of large scale data sets. But recently we have very high end computational resources, which is provided by these NVIDIA GPUs, which can be used as the accelerated computing resources. And also nowadays we have many publicly available large scale data sets which can be utilized to train even a deeper network. So why deeper neural network we could not train earlier? Because if we have a deeper neural network, then actually we will have many more number of parameters. So here I will assume that I'm assuming that basically you might be aware with a basic fundamental of how this neural network is working. So neural network is basically a parametric model which has the parameters in different layers, and we used to train this particular network using gradient descent technique, where the parameters of the model is updated in the opposite direction of the gradient. So there is a method called back propagation. Using that back propagation, entire training happens in multiple iteration. So what happens when we have many number of parameters, then it is very difficult to train such a model with a small scale data set. And at the same time, we need to use more and more computational resources in order to perform the training of such a model for large number of iterations. So that's what has happened in past 1 decade. And especially if we talk about computer vision, then deep learning has come in computer vision area in 2012, when first CNN model was introduced. Basically, CNN model was introduced long back in 1998 by Jan LeCun, which is one of the Turing awardee in artificial intelligence area. But from 1998 to 2012, there was no much progress. And again, due to this particular problem, the bottleneck of limited computational resources as well as non-availability of large scale data set. But what has happened around 2006 and 2007, this Stanford University, in collaboration with other universities, they started accumulation or creation of a large scale data set, which is called ImageNet data set nowadays. And in fact, they started a visual recognition challenge on ImageNet data set, and people used to develop their model, and then basically they just test their model on their data set, and then every year they were announcing the winner of best model. So what has happened in 2012, when the first CNN model that was developed in 2012, and when they tested over ImageNet dataset, then they found very encouraging results, and they found basically error rate just with 16%, which was much better as compared to the non-deep learning based models. So again, question comes now that, okay, why we are saying convolutional neural network? And first of all, how this convolutional neural network is different from a traditional neural network that we might be familiar. So if you again recall that what is a typical neural network? In a typical neural network, we are having different layers, and these layers are also termed as the dense layer. Why this is called the dense layer? Because if we take any neuron in any given layer, then it is connected with all the neurons in its previous layer. So that's why this is called the dense layer. So now here in this particular example that you are seeing in the slide right now, we have only 2 hidden layers here. However, we can have even 50 hidden layer, we can have 100 hidden layer. So based on that, we can say what is the depth of our deep learning models. So this is also deep learning model, but this deep learning models might be suitable for some other type of data. Basically, it is suitable for the vectorized data, where we have the data in a vector form, then that vector will serve as the input, and we can have basically the nodes in different layers, and ultimately what output we want to predict and how many number of output we want to predict. Based on that, we can decide the number of neurons in the output layer. But what happens now if we have an image, and because if you're talking about computer vision applications, then our input is either images or videos. So let's have a simple problem just for the images. If we have image as the input, then, and a very basic problem, let's consider as the classification problem. So suppose if I have this image of the cat and I want to classify this image into cat category, then is it possible to utilize this multi-layer neural network, which is generally used for vectorized data on this image? And this image is not the vectorized data because this is not a simple vector. This is actually a matrix. And in fact, this matrix may have more than one number of channel. And in fact, that is true if we have the color images. So you might be aware that color image is actually built with 3 channels. It's called red, green, and blue channels. But ultimately, image is nothing but matrix, because if we as a human being, we are seeing that, okay, this is a cat. But if we talk about computers, how computer is going to perceive the content of this image? Computer is only going to see the numbers, and these numbers will be in between 0 and 255 if we are having if we are representing each channel by 8-bit depth. So now question comes here, is it possible to give this image as the input to this neural network? Then the answer is we cannot apply this neural network directly on this image because this is not the vectorized data. This is actually having more than one dimension. In fact, it is having a matrix. So what could be some other strategies which actually has been followed also in the literature? We can stretch this image into a column vector, and then we can give that one as the input. But obviously, this can be one of the way to use, but that is not a good way. That is not a right way to proceed because uh, even as a human being, if we are having only one vector, if I just stretch this image into a single vector, then we cannot identify that okay, what object is present inside that vector because we have lost the 2D relationship information. And if we have already lost 2D relationship information in the input itself, then we cannot find very good performance using this neural network models because even some information is already lost at the input label itself. Other ways might be, again, we can extract some features from this input image in a vector form, and then we can give that feature as the input. But again, if we are going to do the same thing, then this is not no more different from the traditional way of processing the images, where first we used to extract the important features and then we used to apply machine learning on top of that. So that's where basically this in order to solve this particular problem, now we have another variant of neural network, and that is called convolutional neural network, which can be used to process this image directly in the matrix domain. So there are different names for the convolutional neural network that people use to refer, like CNN, ConNet, deep convolutional neural network. But at the bottom, convolutional neural network is able to work on these high dimensional data, which is images, due to two properties that actually it incorporates. And these two properties include local connectivity and weight sharing. So if we talk about a normal neural network, a artificial neural network or multi-layer perceptron, then the kind of connectivity that we use there is the global connectivity. And we do not utilize any weight sharing. All weights are independent in case of the uh, multi-layer perceptron, or basically a dense layer or dense network. However, what is the local connectivity? In case of the local connectivity, a neuron in any given layer is not connected to all the neurons in its previous layer. Rather, it is connected to only few neurons, which is in its local proximity. What is the meaning of local proximity here? Local proximity refers basically the position, relative position. So we need to define that, okay, how much local proximity we want. So for example, here you can see in this particular diagram, we have the local proximity of 3. It means that if we talk about the hidden layer, so if you see at the right hand side, then any neuron in the hidden layer is actually receiving the inputs only from 3 neurons in its previous layer. And those 3 neurons are actually the nearest neurons to that particular in terms of the position. It means that those 3 neurons are in the local neighborhood of that target neuron. However, in case of the global connectivity, a neuron in hidden layer is actually receiving the inputs from all the neurons in the previous layer. So now what will happen in this particular case? So if we have the global connectivity, then we can see how many number of neurons we have in the input, that is 7, number of neurons in the hidden units 3, both in global and local connectivity. But now we can compute the number of parameters that we have. So in case of the global connectivity, how many number of parameters we have, and in case of the local connectivity, how many number of parameters we have. So if we talk about the global connectivity, so one neuron is connected to all the neurons in the previous layer. So it means that one hidden neuron is actually having 7 parameters, which is with respect to all the neurons in the input layer here. And we have 3 number of neurons in the hidden layer. And because all these weights are independent, weights are basic. So weights and parameters both are the same thing here. So all these parameters are independent. So we can say that basically we are going to have 21 parameters in the global connectivity. I'm not including the bias term here. If you are familiar with the bias term, so I have just omitted the bias term. However, in case of the local connectivity, because now a neuron is connected with only 3 neurons, it means that we have only 3 parameters with respect to one hidden neuron. But we have 3 number of hidden neurons, so 3 into 3, we are going to have total 9 number of parameters. So it means that if we follow the local connectivity, then we can reduce the number of parameters drastically. And in fact, this is required to reduce the parameters drastically, because if we are going to work with the global connectivity and that too on a very high dimensional data like images, then it will be roughly infeasible even to perform the computation, even with the current high-end computational GPU driven computational resources also. So that's where we need to rely on this local connectivity, which actually facilitates the working with images. Another important thing that a convolutional neural network adopt is the weight sharing. And what is this weight sharing? So now here we can see in the left hand side, we have the diagram without weight sharing, and then the right hand side, we have the diagram with weight sharing. So in case of without weight sharing, all the parameters are treated independently, means these are independent initialization, they are learning independently. But in case of the weight sharing, what happens? Suppose if a neuron in the hidden layer is having 3 parameters, W1, W2, W3 with respect to 3 neurons in its previous layer, then the same weight will be also used by the other neurons in the same hidden layer. So here you can see the middle neuron also having the same weights W1, W2, W3. In fact, the last neuron is also having the same weight W1, W2, W3. It means that it means that all these neurons are actually going to share the weights. So what is the advantage? The advantage will be in terms of the number of parameters, which is going to be reduced further drastically. So now if you see number of parameters without weight sharing was 9, but number of parameters with weight sharing will be only 3 now. So now we can see the number of parameter reduction means originally we had 21 parameters when we did not use weight sharing as well as local connectivity. But after using local connectivity and weight sharing both, the number of parameters is reduced from 21 to 3. And that's where basically the computational requirement will also get reduced, and we will be able to process image itself directly by this neural network. So typically, a convolutional neural network is having different layers, and the main important layer which actually facilitates the entire working of this convolutional neural network is the convolution layer, which is represented by con here. We also have other layers like non-linearity layer, that is ReLU, rectified linear unit. There is a pooling layer which is used to reduce the spatial dimensionality. And we also have FC, which is called the fully connected layer, which is equivalent to the dense layer that is used in even normal artificial neural network. So a minimum of one fully connected layer is compulsory to have, because that is going to serve as basically the last layer in order to produce the classification score for different classes. So now here we are going to see the different layers. So input layer is input image itself here, so we need not to discuss much on input layer. Now we will see how this convolutional layer is going to work, and what is non-linearity layer, why it is required, what are the popular non-linearity layers, that is activation function, what is pooling layer, what is fully connected layer. So fully connected layer we have already seen, this is nothing but the dense layer, and classification layer, that will be basically the softmax. So if we talk about the convolution layers, and if you have your background from image processing, and if you are familiar with the filtering concept, then this is very easy for you to understand. And but if you don't have such background, then also it is going to be much easier for you to understand, because this is a very simple concept of just filtering. So where we have some input and we have some kernel function, and we are basically going to slide this kernel. We are going to superimpose the kernel, and we will do some operation which is nothing but just performing the dot product, and then slide over entire spatial resolution and compute the values. So how this is going to work? So now we are going to have a filter, which is also called kernel, uh, and this is also called the parameters or the weights. So basically, we have here 5 cross 5 cross 3 filter. So these are actually the parameters. So it means that we are going to have 5 into 5, 25 into 375 number of parameters. It means, but what will be the values of these parameters? So initially, when we are going to start training of our model, then the values of these parameters will be initialized randomly. And then after that, these values of these parameters will be updated in every iteration of the training by utilizing this gradient descent based backpropagation technique. So now what we are going to do with this filter. So now if you look over the filter dimension, then the filter dimension is 5 cross 5 cross 3, where 5 cross 5 is a spatial resolution and 3 is the number of channel in the filter. So one thing is fixed here. The number of channel in the filter is exactly same as the number of channel in our input. Suppose our input is an image and that image is having a spatial resolution of 32 cross 32 and 3 channels corresponding to red, green and blue. Then in that particular case, our kernel will also have 3 channels. But spatial resolution of the kernel is again design choice. Someone can have 3 cross 3, someone can have 5 cross 5, someone can have 7 cross 7. So that basically we can find out for our problem what kernel size better suits. But how this convolution is going to happen here? So basically in convolutional neural network, we used to say that this is convolutional layer, but at the end when it comes to the implementation, then instead of doing the convolution, we simply used to do the filtering that is called cross correlation. So what we will do now, we will take that filter, we will superimpose that filter with our input image. Means if our filter dimension is 5 cross 5, then we will take a 5 cross 5 region from our input image and all 3 channels, and then we will perform basically just dot product, which is written as W transpose dot X plus B here. If we consider this W as the parameters, which is nothing but 75 values in the filter, and similarly X is 75 corresponding values from the image, and then just doing the dot product and plus a bias term. So for each filter, we will also have a bias term, which is also a parameter. So now this is going to give us a single value in our output. Now what is next we need to do is to slide this filter, the same filter with the same value, we need to slide over entire spatial resolution. So how we will slide that you can see into this diagram, which is at the right hand side here. So now if we assume that this
सर आपकी स्क्रीन विजिबल नहीं है.
स्क्रीन विजिबल नहीं है
हाँ,
सर?
मतलब विंडो विजिबल है आपकी.
विंडो विजिबल है
आपको
शुरू से
विंडो
ही? सर शुरू से ही विजिबल नहीं है?
नहीं, अभी जस्ट अभी.
अच्छा अभी?
हाँ, जस्ट अभी शुरू हुआ है. अभी तक तो
अभी
आपकी
आ
स्क्रीन
रहा है?
विजिबल थी. हाँ सर, मेरे ख्याल से आपने शायद कोई दूसरी विंडो आपने खोल रखी है. अभी जो हम लोग को विजिबल है वो आपका जो आपके स्क्रीन पर आ रहा होगा ना MS टीम्स का, तो वो दिखाई दे रहा है. अभी कंटेंट्स दिखाई नहीं दे रहे हैं स्लाइड्स के.
इसके पहले दिखाई दे रहा था सर?
जी जी सर.
स्लाइड शेयर नहीं हुई है, स्लाइड शेयर कर दीजिए.
अभी बताइए सर.
हाँ, यस सर, नाउ इट इज विजिबल. अब ठीक है, अब स्लाइड्स विजिबल है.
Okay, sorry for this interruption. So basically in case of the convolution layer, we have a filter, and that filter is having some dimension. It will have the spatial resolution as well as number of channel. So the number of channel in the filter will be same as the number of channel in our input. And a spatial resolution, this is design choice that we have to set based on our observation or our experience. So now if we just superimpose this filter to our image at a particular location, then it will basically consider the same area, and if we just do the dot product, then it will produce a single value as the output. So basically in order to produce entire channel as the output, what we need to do, we need to take this filter. Now you can see in the right side figure. So this filter we need to now just superimpose at the extreme left and top corner, and then after that after doing this operation, we need to shift it by one position, and then again do the same dot product, then again shift by one position. And once we reach to the last, then we need to repeat for the second row. So like that, basically, if we just slide this filter over entire spatial resolution and compute the values, then ultimately we will end up with one channel of the output. So now we will basically have one channel in the output. Note that the spatial resolution of this channel is decreased here. Originally we had 32 cross 32, but now we have only 28 cross 28. And the reason is because we are not using any padding here. If we are not using any padding, then we need to leave some number of rows and columns, because we will not have sufficient values in order to perform this particular dot product operation. So if we have 5 cross 5 kernel, then we need to leave 2 rows and 2 columns. So basically there will be reduction of 4 in the spatial resolution. So that has become 28 cross 28. So this is just one filter. Similarly, we can have one more filter. And then if I just repeat the same process with another filter, then I can generate one more channel in the output. So now someone can have this question here that, okay, why we should repeat suppose in the filtering, I have a filter of detection of the horizontal edge. Then what will happen if I just slide that filter over entire image? Then it will give us the output only to that particular location where horizontal edge is present in the input image. But what about other information? Other information is lost. We do not have that information in our output. So that's where we cannot manage with only one filter, because one filter can produce only a special type of characteristic in our output channel. So that's where we need many number of filters so that we can extract different type of information from our input images. So we can use more and more number of filters. And again, this is based on what is the problem that we are solving, what is the complexity of our problem, and how much computational resources we have. So based on all these criteria, basically we have to decide this in a very cautious way, that what should be optimum number of filters that we can utilize. The filter dimension and number of filters both are information over entire image spatial resolution, then basically it is going to produce a feature map. In that feature map, we have the higher values with respect to those locations where we are actually having similar information that we are looking for through that particular kernel or that particular basically weight matrix. Similarly, if we have some other kernel, then this is going to produce output with basically different features extracted. So like that, we can have many number of features. And in fact, in early days, this bank of key number of filters are basically, there was Gabor filters, there were many filtering techniques and bag of filtering techniques that people have utilized in order to extract different meaningful features from the input images. But now, ultimately, what are the features that we extracted earlier using these filters was manually designed, means the weight matrix of those filters were designed manually by the experts. But what is happening in case of the deep learning here in convolutional neural network, we are not saying to the network that, okay, you extract horizontal edge or you extract diagonal edge. We are not saying any such thing to our network. We are saying that, okay, this is the random values. This is the random values of the filter. You automatically learn from the data that, okay, what type of information is basically majorly present in this particular data set that can lead to the higher accuracy for our problem. You identify that characteristic automatically and extract such information using these kernel functions. So this is again just illustration that, okay, how this filtering is happening here. So like that, we have the filters. We have the filters. Filter is also having 3 channels. So these are the values of the filters, like -1, 0, -1. So So what we need to do here, we need to basically take the corresponding values from the input images, corresponding channels, just do the dot product, add the bias term. So this is going to give us one value in the output, which is -3 here. Similarly, if we just slide by 2 position here and again repeat the same process, now this is going to give us -1 basically here. So like that, basically, if we just perform, if we just do this dot product by sliding this particular kernel over entire spatial resolution, then we will be able to produce these output maps. So now this is one layer that we have seen here. Our input is an image of dimension 32 cross 32 cross 3. We have a convolution layer of size 5 cross 5 cross 3 having 96 kernels, and it produces an output map of a spatial resolution 28 cross 28 with 96 channels. But if we talk about a deep convolutional neural network, then we need to have many number of such convolution layers. And if we have, suppose if I want to have one more convolution layers, then what will be input to that convolution layer? So actually the activation map that we have generated now will serve as the input to the next convolution layer. And if you are going to perform one more, if you're going to use one more convolution layer, then and suppose if spatial resolution is again 5 cross 5, then the number of channel in that convolution layer should be exactly same as the number of channel in our input. But now this feature map that we have will serve as the input. So we have 96 channels in the feature map. So our kernel will also have 96 channels. So you can see here the dimension of the kernel is now 5 cross 5 cross 96. And now again, if we just perform this particular dot product of this entire dimension 5 cross 5 cross 96, then it will produce a single value in our output channel, and that too in one channel. And if we again just slide it over the entire spatial resolution, we will have one channel in the output. And again, because we are not using any padding, the spatial resolution is decreased from 28 to 24, but we have only one channel. So again, we can use more and more number of filters in order to have more channels in the output. So for example, if I use 128 number of filters of same dimension, now I can produce 128 channels in the output map. So now here you can see that, okay, what could be the complexity, what could be the computational requirement in order to produce a single value here, how much computation we are doing. Basically we are doing 5 into 5 into 96 mean that many number of product, and then after that that basically equivalent number of the summation in order to produce a single value in the output, and that too how many times we are repeating the same process. So that's where and what is going to happen if you have a high resolution image, let's say 256 cross 256, then the number of times you are going to slide over the spatial resolution is going to increase, then your number of operation is also going to increase. So that's where this convolution layer is going to be very computationally complex. So that too, if we are having the local connectivity, suppose if there is a global connectivity, means in order to produce a single value in the output map, if I want to do the dot product with all the values in the previous layer, then now you can assume that, okay, how many number of operations will be required, and in fact it will be roughly infeasible to perform such operations. So we can have now a multi-layer convolutional neural network where we can have many such convolution layers in between. Obviously, in between these convolution layers, we may have some other layers as well, like we can have non-linearity layers, we can have regularizer layers, we can have pooling layers, so we can have different other layers in between these sequence of convolution layers. So now here we can again argue that how this convolution neural network is making use of two important properties of local connectivity and weight sharing. So what is happening? In order to produce a single output in output channel, here we can see how many number of input values are used. So suppose if my kernel dimension is 5 cross 5, then actually I'm using only 5 cross 5 window, spatial window. It means that in order to produce a single value as the output, we are only relying on its local neighborhood in the input map. So that's where this local connectivity is utilized. And about weight sharing, because if we have a kernel, we are sliding the same kernel over entire spatial resolution, and we are producing all the values in a particular channel in output. So it means that the same weight being used in order to produce the entire channel, and that's what is the concept of filtering. So basically it is making use of this weight sharing. At the same time, these convolution layers are also very much flexible in order to deal with any number of input channels. So for example, if we have X number of input channels, then we can just extend our kernel also with X number of channels and it can just utilize it. We can also produce any number of output maps that, for example, if I want 128 number of channels in the output map, then I can have 128 number of kernels and each kernel can produce one channel. So I can have 128 channel in the output map. So we can also have a look over this spatial dimension. So there is something called stride when we are basically utilizing this filtering concept. So stride means after doing one dot product, by how many position we are shifting. So by default it is 1, means we are just shifting by one position and again performing this convolutions. But in practice, even people can follow even stride 2 or stride 3. So based on that, what is image dimension, what is kernel dimension, what is the stride, we can find out what should be the output size that can be computed as n minus f divided by stride plus 1. So what happens here? We have the input dimension as 32 cross 32. And if we use convolution layer of 5 cross 5, then our input spatial resolution is decreased. And suppose if I want to I want to develop a 50 layer deep convolutional neural network, then this is not possible to create such a convolutional neural network in present setup, because what is happening, 32, then 28, next 24, next will be 20, 16, 12, 8, 4. So after that, our spatial resolution is collapsed. So that's where if we want to have a deep convolutional neural network, then we need to basically retain the spatial dimensionality such that we should not shrink very fast. So in order to do that, there's the concept of padding. So basically we should perform the zero padding in order to retain the original input dimensions. So how many number of zero padding is required, that depends upon the kernel dimension. So suppose if my kernel dimension is 3 cross 3, then only one zero padding is sufficient to produce the same size output. If kernel dimension is 5 cross 5, then we need 2 zero padding, means 2 rows and 2 columns each side. Similarly, if kernel dimension is 7 cross 7, then padding will be 4 rows and 2 columns each side. So this is very important to understand that what is the kernel dimension and what is the kernel size. So basically we can compute the number of padding amount by using this input dimension plus padding amount 2 times, because we are doing this padding on the top and bottom both and left and right both. So basically we can compute it by this particular very simple formula. What is the original dimension of our input plus 2 times padding amount minus what is the dimension of our kernel size divided by the stride plus 1. So using this we can compute the number of we can compute the output dimension. The number of channel in the output is very simple to compute. That is nothing but the number of kernel that we are using. We can also compute the number of parameters also. So the number of parameters can be computed as what is our kernel. So suppose if my kernel size is f cross f, then it means that I have f into f number of parameters just in one channel. And how many number of channels we have. So for example, if I am having d1 number of channels, then it is going to become f into d1. So that many number of weights per filter. And how many number of filters we have. So suppose if we have k number of filters, then the total number of parameters will become f into d1 into k. And for each filter we can have one bias. So for k filter we can have k number of bias as well. So the total number of parameters will be f into d1 into k plus k. So this is very simple in order to compute this output dimension as well as the number of parameters in any convolution layer. So this is about the convolution layer. Other layers that we have is the pooling layer. This is also one of very important layer where many times we need to reduce the spatial dimension. So, and why we need to reduce the spatial dimension? So this is the practice in deep convolutional neural network. that if we are increasing the number of channels, then we should decrease the spatial resolution. Because if we are having more and more number of channels with higher spatial resolution, then computational complexity will increase drastically, and it will be very difficult for our current resources to perform the computation for such network. So that's where if I want to use 256 number of channels, then my spatial resolution should be somewhere 32 cross 32 or 28 cross 28. If I want to use 256 number of channels and at the same time my spatial resolution is also 256 cross 256, then it will become very cumbersome for in order to perform the training. So there are many pooling techniques, but one pooling technique which is very common in practice is called the max pooling, where we retain the maximum value in a local neighborhood and discard the rest of the values. So for example here, so suppose if this is our input feature map for one channel, and if I want to apply this max pooling on a 2 cross 2 this region with a stride 2, then what will happen? I will take a 2 cross 2 region here, which is having value 1156. I will contain only the maximum value, which is 6, and throw away 511. Similarly, now taking the next 2 cross 2 window, because stride is 2, so in next 2 cross 2 window 2478, so we will retain 8 and throw away 724. Similarly, we will do for others also. So now one question comes here that, okay, we are retaining the maximum and throwing away others. Are we not losing much information? So the answer here is obviously we are losing information, but still we are retaining most of the useful information. And why? Because whenever this max pooling is going to be applied, generally it is applied on the output of the convolution layer. And we know that in convolution layer, basically we are performing the filtering. And in case of the filtering, we are getting higher outputs to those locations where we are having such input, which is basically which we are looking for through our kernel. So if we are retaining those maximum values and throwing away other values, then actually we are retaining the information that our kernel is looking for. So that's where we are losing the information, but we are not losing much information through max pooling, and it is very heavily used in the practice as well. We can also compute what is the output dimension after pooling layer, which is very simple to compute. Again, that what is our input dimension minus kernel size divided by stride plus 1. That will give us the spatial dimension. And how many number of channels? Now we are not actually touching upon the number of channels. So if we have d number of channels in the input, then we will also produce d number of channels in the output as well. Fully connected layer, basically this is the dense layer where a neuron in any layer is connected with all the neurons in its previous layer. So this is generally used towards end of the convolutional neural network. Means we will have, after performing some set of the convolution layers, we will basically perform the stretching. Means we'll just convert that feature map into one vector by stretching it, and then we will pass to fully connected layer. And the final fully connected layer will be basically the classification layer, which will produce the class score for different classes. And for the last fully connected layer, number of neuron will be exactly same as the number of classes. Another type of layer which is actually very important in entire deep learning is called non-linearity layer. And in fact, if we do not have non-linearity layer into any deep learning model, then that deep learning model is useless, because it will not be able to learn any non-linear mapping. And in fact, in real scenario, we are having all these parametric models. Basically, we want to learn a transformation function from our input domain to some latent space where we can have better separability in the feature space. So that's where this non-linearity layer is very much important, and that is achieved through the activation functions. We have many activation functions, and here again we can see that, okay, what is the usefulness of these activation functions? So for example, if we have more and more number of neurons, then we actually have a more and more number of activation functions, because for each neuron we are going to have the activation function. So if we have less number of neurons, then we have less number of activation function, means less non-linearity. Then in that particular case, what will happen? Our model cannot learn a complex decision boundary between different classes. However, if we can have more and more number of neurons, then our model is having the capability to learn even non-linear decision boundaries. So here you can see the non-linearity in the decision boundaries increased if we have 600 neurons. And if we have even 20 hidden neurons, then it further improves. Means we have even much better non-linear decision boundary if we have more and more number of activation functions. So this non-linear decision boundary means basically we are able to segregate the data which are basically having a very similar distribution, or it is very hard to find out a linear classifier in order to separate these data into different categories. And that's where basically these non-linear decision boundary comes into the picture. So there are many activation functions, like there is a sigmoid activation function which was used in early days when neural network was there, but it has some major problems which is basically related to this gradient diminishing problem that we are not discussing in detail. There is a tanh activation function which is also extension of this sigmoid activation function. Instead of squeezing in between 0 and 1, tanh activation function produces the output in between -1 and 1. But it also has the same problem, that is a gradient diminishing problem, because if we have this larger inputs either in negative or in the positive regime, then we can see that this is kind of a flat surface. This is a flat region in case of both, either it is sigmoid or tanh, it is relatively flat. And if you have a function which is flat in the horizontal direction, then we know that gradient will be roughly 0. And if gradient is roughly 0, then this is going to basically be problematic when we perform the back propagation through gradient descent, where gradient has the major role. So in practice nowadays, basically, if we talk about the convolutional neural network, the deep learning, then this ReLU, which is called rectified linear unit. So this particular activation function is very common. And this activation function is a linear activation function, but there is a non-linearity, or there is a rectification only at 0. Basically, this ReLU activation function is identity function for the positive inputs, and it is 0 function for the negative inputs. So basically, all negative values will be converted to 0, and all positive values will be passed as it is by this ReLU activation function. So what is the good thing with this activation function? This is much more faster because it doesn't involve any sophisticated function. This is just identity function or 0 function. And but the problem with this ReLU activation function is, again, this dying gradient problem for the negative inputs. And in practice, in spite of having this particular drawback, in practice ReLU works very well, and it is still by default design choice in most of the convolutional neural network. There are many other activation functions proposed in the literature. We are not going in very detail. If you are interested, you can have a look later on. But one of recent activation function which became very popular was Swiss activation function. And the Swiss activation function was one of the adaptive activation function, which can adopt its shape based on the complexity of the data set as well as the model that we have. So either it can, basically it can be in between the linear function as well as the ReLU activation function. It can adopt its shape based on a parameter which is part of the activation function itself, which is represented by beta here. So this is given as x into sigmoid of beta x. So in case of the deep learning, there are regularization techniques, because many times we find that these deep learning models tend to overfit the training dataset and performs very bad on the test dataset. So that's where this regularization techniques is very heavily used in these deep learning models, including CNNs. And some popular regularization techniques are like dropout, where we can drop some neurons randomly at the training time, and basically then it can serve like ensemble of sub networks. And basically if any suppose if some set of neurons are trying to overfit some type of characteristic, and but it is not guaranteed that that particular neuron will be present always. It may drop randomly at any point of time. So what will happen then? The dependency on only set of neurons will not be there, and that's where this is going to become much more regularized, or basically the overfitting will reduce. Similarly, there is another technique which is very common for regularization, is called batch normalization. So in case of the batch normalization, we want the batch of data that we are processing in the feature space also it should basically have close to zero mean and unit variances, that we can have a kind of a Gaussian nature in the feature space, which is much more beneficial when we are performing these operations in case of deep learning. So obviously, based on the problem that we are solving, we need to also include some objective function, and that objective function will be based on, okay, what we want to do, means how we can measure the goodness of our model. So for example, if we are having a classifier, if you are having a classification problem, then we can utilize like SVM classifier or softmax classifier, which is also termed as cross entropy loss. Similarly, if we want to perform the object detection, then we can have the regression loss. If we want to do the segmentation, then again we can have different losses for different type of. So in summary, we have basically different layers like convolution layer, non-linearity layer, coding layers, and this regularization layer. So all these layers are arranged in an hierarchical fashion, and ultimately it leads to a network which is called convolutional neural network. At the end, we have a specialized layer based on our problem that we are solving, and ultimately we can train this entire network using this gradient descent based optimization technique. So the growth in this computer vision area, basically in convolutional neural network, was heavily driven by this ImageNet challenge. So this ImageNet challenge was one of the initiative that was taken to create a larger data set, and in fact also host this large scale visual recognition challenge, which is called LSVRC. And as mentioned earlier, the success is basically due to the availability of high-end computation nowadays using GPUs plus large scale data sets. This is the progress on ImageNet challenge. So in 2012, we got AlexNet, that was first CNN model that gave 16.4% of the error rate, that is called top 5 error rate on this ImageNet classification challenge. In 2013, we got in next model, which is called ZFNet with 11.7, which is very similar to AlexNet with minor some this hyperparameter optimization or basically customization. In 2014, we have Vcc Net that was not winner. It is kind of a second winner, but due to the simplicity of this model, it became very popular with 7.3% error rate. And in 2014, we have the Google Net, which is basically from Google with 6.7% error rate. 2015, we have the residual network with only 3.57 error rate. And in fact, the performance of this residual network was even better than the human level performance. So on this particular data set, the human level performance was 5%, but ResNet has even surpassed the human level performance with just 3.57% error rate. 2016, the winner model was the ensemble model of ResNet and GoogleNet called version 4. In 2017, we have the squeeze and excitation network with 2.251% of the error rate. So where is the where is the major advantage here? So now if you see in 2012 itself, the best model, the best non-deep learning based model on this particular data set gave the performance, the error rate as 26.2%, but this deep learning based model gave the error rate as 16.4%. So there was a difference of 10%, and a difference of 10% in the error rate was a very, very significant difference. So that's where after 2012, entire computer vision community that people were working, they entirely shifted on this convolutional neural network. And nowadays, if you are working in computer vision area and you are not using convolutional neural network, if you are using traditional pipeline of computer vision technique, then it is very difficult nowadays to get any publication at any reputed place. So this is basically just about convolutional neural network. Now, there are many convolutional neural network architectures for different problems. I will not go in very detail to these, but I will just show you what are the different popular models here. So for classification, as I already mentioned, there is a AlexNet model. So AlexNet model was was the first CNN model that became very popular for basically computer vision, and that came in 2012. And basically, it is having a series of this convolution layer, max pooling layer, normalization layer, then again convolution, max pooling, normalization, then convolution layers, max pooling, and then some fully connected layers. And the end, last fully connected layer is having 1,000 neurons because it was used for ImageNet dataset, which was having 1,000 categories. Similarly, this Vcc network came. So Vcc network, so what was the difference? Major difference from AlexNet to Vcc is more and more number of layers. Basically, the model were becoming deeper. So in case of the AlexNet, there was only 8 layers, but in case of the Vcc, number of layers were increased to either 16 or 19. And this Vcc was also a very simpler model, means it was having kind of a very symmetric architecture. Whenever convolution is there, it uses only 3x3 kernel size, stride 1, padding 1, 2x2 max pooling, always is stride 2. And basically, due to its simplicity, it became very popular. So this Vcc net was basically proposed from this visual symmetric group of this Oxford University. GoogleNet also became very popular due to its computational efficiency. And this GoogleNet was first kind of inception model that combined the different combined max pooling as well as convolution with different kernel sizes in the same unit, which is called the inception module. So what it does, basically it uses 1x1 convolution, 3x3 convolution, 5x5 convolution, as well as max pooling, and combines everything in the same layer. And it uses a bottleneck layer, which is called 1x1 convolution, in order to reduce the number of channels with minimum number of computation. And ultimately, it just basically stacks these inception module on top of each other, and it is able to perform very well in practice with very computational efficiency. Similarly, ResNet. So ResNet was one of most important development that has happening in entire convolutional neural network, because we had this we had AlexNet, we had VCCNet, we had GoogleNet, but the number of layers that we can use with these networks was limited. We cannot train a very deep network that is on the similar line of AlexNet, VCCNet, and GoogleNet. And the reason was because if we have more and more number of layers, then during backpropagation, the gradient diminishing problems comes into the picture, and it is very hard to optimize such a network with many number of layers. In order to avoid this particular problem, this residual network came into the picture, and this residual network basically creates a kind of identity mapping. It means if we are transforming from X to Y, then basically this Y will be the transformation fx plus X. It means that the input X is directly provided as the input even in the transform domain also. So what is the advantage of this? So during back propagation, when we are going to compute the gradient, so what happens, basically due to this identity function, we know that if there is a function y is equals to x plus fx, then for this particular path, which is the identity function, the gradient is going to be unit gradient. It means that whatever gradient we are getting here, and local gradient is going to be basically a unit gradient, then there will not be any loss in the gradient. If we are basically, in other words, we can say this identity mapping or identity connections are going to serve as kind of a highway, for the gradients to flow back from last layer to the first layer. So that's where basically it tackles this gradient diminishing problem in very deep convolutional neural network. And that's where this ResNet model, even people have trained 1000 deep ResNet network as well very successfully. There are other architectures, CNN architectures for other problems as well, like object recognition problem. So in case of the object recognition, basically we want to first find out where is the object. Means we can have multiple objects in the picture. We want to find out where is the object, and then after that we want to find out its category. So for that, the model which became very popular was this reason proposal and CNN features based model, which is called RCNN. So basically what it does, basically it first find out some probable reasons from the image, and then it extracts those reasons and then performs some kind of normalization, and then uses the convolutional neural network on top of that, on top of each reason. And ultimately there is a classifier on this convolutional neural network for all these different reasons, and it can basically give the classes for these different regions that we are processing. So there are many other variants of these RCNN models, like there is a fast RCNN model where instead of doing this cropping in the input domain, the cropping can be done in the feature domain. Means the convolutional neural network, instead of applying on different regions independently, it can be applied on entire image itself once, and then cropping can happen in the feature space, and rest of the process can be very similar to the RCNN. However, but this RCNN and fast RCNN both rely on basically these regions, and these regions are extracted using some other technique, which is the manual technique. And this particular problem is removed in faster RCNN model. That was the next version of RCNN, where the network itself is having a mini network, which is called a reason proposal network. And this reason proposal network is basically working based on, again, this filtering and the sliding concept, and it finds out the probable reason in the input image that can have some object. And based on that, basically, it is able, this particular model is able to work in. So instead of relying on some other algorithm to give us the information about the probable reason where object might be present, this network has a mini network inside the network itself that is called reason proposal network to identify such reasons. But all these models are basically called two-stage models, which is in one stage it finds out the probable reasons and then process those reasons to do the final to compute the final results. Due to that, basically these models are computationally a little bit complex, and in order to do these object detection in real time, there is a one-stage model, and YOLO is one of the popular model that is called you only look once, where instead of computing the proposals or the reason proposals or the box are the basically different reasons first and then process, this YOLO takes input itself as the input and just produces one tensor of prediction as the final output. So basically it just does everything in just one sort of mapping. So this is very efficient, but this is having the lower accuracy because this is a single step process. Then it is also possible that it may not be able to basically work very well with different scale of the objects that we have. Similarly, there are different signal architectures for the segmentation problem. So segmentation problem means we have an image, we want to create a segmentation map for that image. So a popular model for that is called fully convolutional model. Means now here you can see we have an image as the input, we want to produce a segmentation map, which is called semantic segmentation map as the output. So now if you see, in case of the classification, our final output is just class label. In case of the object detection, our output is a bounding box and then class label. However, in case of the segmentation, our output itself is going to be another image of the segmentation map. So that's where basically an entirely different type of convolutional neural network comes into the picture, which is called basically encoder-decoder based model, where we have the convolutional neural network, which first reduces the spatial resolution and increases the number of channels. But after that, we perform the reverse operation of that, which is called up convolution, or basically upsampling, where we slowly decrease the number of channels and increase the spatial resolution such that the final output channel can have exactly same spatial resolution as we have for our input, and then its output can be treated as basically the segmentation map, and based on that we can compute the error, and that error can be back propagated, and based on that we can train this entire model. There are many other variants of such networks, like we have the unit. So in case of the, so unit is one of very popular model. So what unit does basically, when we are performing the downsampling, then whatever is the feature map that we are producing, those feature maps are also available at the time of upsampling. So basically it is concatenated with feature map that we are getting basically from this downstream process, and then ultimately the entire processing will happen. Similarly, we have another network which is also very popular called SegNet. So SegNet is also very similar line, having encoder decoder based model. So encoder is basically convolutional neural network that is downsampling. Decoder is also convolutional neural network but upsampling. So one important thing in SegNet, because it uses the max pooling layers, so it basically remembers that what was the position at which we got the maximum value in the max pooling, and it utilizes that location at the time of unpooling. So that's what is one of the important characteristic that is utilized in this SegNet network. Another important network in case of the semantic segmentation is basically this mask RCNN, which is basically utilizing this faster RCNN concept. So it extends the faster RCNN. Basically, it finds out the class labels as well as the bounding box for the by utilizing the faster RCNN.
Sir, your audio is muted.
Sir, you are not audible.
Oh, somehow I was muted. I don't know how.
Okay, sir.
Okay. So I think now we are running out of time, so I will try to close it in next 2-3 minutes. So yeah, basically this is another type of network where we have two networks. So generator networks tries to generate better and better samples, and discriminator networks tries to distinguish between generated samples and the real samples. So the same can be extended even to image to image translation, where we can translate image from one domain to another domain. So for example, here, this is one example to translate the image from sketch to the photo. So we have the generated model. So this generated model can take image in one domain as the input and can generate image in another domain as the output. So again, this is very similar to like unit model or siGnal model, where image can be as the input and image can be also as the output. So this is basically called pix-to-pix model, which is very popular. Another model which is very popular is the cycle GAN model, which is for unpaired scenario. So pix-to-pix is for the paired scenario where we have the input image and the target image. Both are exactly paired. But if there is not, if exactly pairing is not possible, then we can have the cycle GAN where transformation happens from input domain to output domain, and again we will do the back translation from output domain to input domain, and basically we will reconstruct again in the input domain, and then we compute the cycle consistency loss between the original and reconstructed version, and based on that the model is trained. So yeah, that's it about this particular session here. So we just have had a brief of convolutional neural network, how convolution layer is basically working, what are different layers and what is the uses of those layers, and what are different, just basically the names and a very quick introduction of different networks, that is CNN models, which is very popular and proposed for different computer vision applications. So with this, now basically this is, if you have any questions, then yeah, I will be happy to take those questions.
Any question from the participant side?
Yes, sir.
Yes, please.
Yes, actually, how can we decide the hidden layers to extract effective features?
I think that we do not have to decide, that network will learn automatically. We need to only decide means what is the kernel size and how many number of kernels we are using. So rest of the things means those values are going to be initialized randomly. There are different initialization techniques. So for example, this JVR initialization technique is very common, which is generally used by default. And then when we are training the model, suppose if you're training your model for 200 epochs, so your parameters are going to be updated in every epoch. So ultimately we will have the final model, which is the final filter, which is going to extract the feature, and that feature will be important to that particular problem that we are solving.
Okay, thank
So
you.
is it clear or not?
Yes, yes, thank you so much.
Yes.
Any other question? So I think there is no question from the participant side. And on behalf of the organizing committee of Amalgam 2021, I am very much thankful to Dr. Shivram Dubey that he took out time. He took out his time from his busy schedule for this lecture. And I am sure that most of the participants must have gained knowledge from Dr. Shivram Dubey. So thank you, sir. Thank you very much for your presence and for enlightening the audience. Thank you, sir.
Thank you very much, sir, for inviting for this particular session, and thank you very much to all the participants for attending the session. Thank you, sir.
Thank you, sir. There is an announcement for the participants that most of the participants are asking for the attendance link and the feedback link. As I informed you yesterday that we are recording all the sessions, so there is no need to worry about the attendance. And as far as the feedback link is concerned, on the 31st, it means on the last day of this workshop, we will circulate the feedback link. So those who fill the feedback form will get the certificate. So I think you do not need to worry about the certificate, about the feedback link and the recording of the sessions and attendance. So also some of the participants are asking for the contents or for the material the authors are presenting, the speakers are presenting. So I would like to inform you that as I informed you that we are recording all the sessions. So at the end of the sessions, at the end of the workshop, all of these sessions or recordings will be uploaded on the YouTube channel of IEEE Young Professionals. So you can access all the contents from the YouTube channel. I will also send the link of the IEEE Young Professionals YouTube channel. I will send the link and you can access all the recordings from there. Okay, thank you. So tomorrow for tomorrow, I will send the link, and tomorrow we have only one lecture and the lecture will start at 3:30 p.m. The lecture duration is 1 hour. It means the lecture will start at 3:30 p.m. and it will end at 4:30 p.m. Okay, thank you all. Thank you for joining us.
Okay, thank you.
Thank you, sir. Thank you.